Hi folks, this is the lecture 21 of the Mechanical Vibrations course in summer of 2024. Let me quickly remind you what we did over the past 2 weeks. We started the subject of multi-degree of freedom system, and we specialized to the case of 2-degree of freedom system because that's the only situation where you can actually manage to some extent hand calculation type problems. Now, in the first lecture, I derived the equation for 2 degrees of freedom system and showed you what the mother of all equation is. And then we solved that problem for a free vibration, but we did not include any damping in the problem. Actually, I'm trying to see. Yeah, we did not include any damping. We left out the concept of damping until the lecture that you're going to see today. So I did the free vibration for you, no damping, and the key point was to be able to use a modal matrix to decouple these equations. Now, once they were decoupled, every single one of them actually became similar to what we had done in the first 6-7 weeks of the course, namely single degree of freedom system. Now, in the previous lecture, I also considered the forced response of a 2-degree of freedom system. In other words, some forces acting on one of the masses, and we again ignored damping, so we solved the forced undamped response of a 2-degree of freedom system to any kind of loading. Okay, again, the whole premise was based on the ability for us to decouple these equations using the modal matrix. Okay, so the lecture today, we want to be able to include the damping, and we're going to do that 2 ways. One of them is called modal damping, and the other one is Rayleigh damping or proportional damping. And towards the end, we talked about the issue of resonance, which it is to some extent similar to what we did for single degree of freedom system, but there's a caveat. You have to be careful because it is possible that the driving frequency match the natural frequency, but still there is no resonance. So there is a caveat there that we're going to discuss in the last 10 minutes of the presentation.
Is how to incorporate damping for a 2-degree of freedom system, and in general MDOF. And there's going to be 2 approaches. One of them is called modal damping, and the second one is called a proportional or Rayleigh damping. Now, once we do that, then we're going to go back to the forced response of a multi-degree of freedom system when there is damping involved. Okay, and finally we talked about the issue of resonance for a 2-degree of freedom system. Okay, so now there are 2 ways that we can incorporate damping into problems. Okay, what we did is, for example, if you go back to a single degree of freedom system, SDOF, we incorporated damping using the viscous damping model. And the advantage of doing the viscous damping model is that the equation remains linear. Okay. On the other hand, if there are other type of damping that are involved, for example, a frictional damping, or what we refer to as Coulomb damping, the equation becomes nonlinear if you try to incorporate that directly. So what we did instead, in those cases, we came up with an equivalent, a viscous damping model, which replicated that Coulomb damping in a sense that the energy dissipated per cycles, they were the same. And going that approach is that we can still solve linear equations, but it inherited stuff from the Coulomb damping in an approximate way. Okay. Now, when we have 2 degree of freedom system, the mother of all equations will be a diagonal mass matrix times the modal degrees of freedom plus a diagonal stiffness matrix times the modal degrees of freedom. In the case where it's multiplied by the mass matrix is going to be, of course, the acceleration, the second derivative of the modal degrees of freedom. Now, what we did in the last 2 days is we carefully eliminated that damping term. The damping term is, in the mother of all equation, is Cx dot. Okay, so notice that when we discussed this thing on Thursday and Tuesday of last week, we left out that damping term. But we can just throw in that mother of all equation, decoupled mother of all equations, 2 terms like this. And these look familiar because when we did SDOF, this is what we got for the damping term once we divide it by, M, and then use the damping ratio. We had a term like this, okay? 2 zeta damping ratio times the natural frequency times the velocity of the point. Okay. Now here we have obviously 2 degrees of freedom, so we just throw this in and throw that in the 2 equations that we have. And instead of this, which is the decoupled mother of all equations without any damping, we're just going to well, keep in mind that this is fine. There's nothing wrong with it, except that if you divide by M1 and you divide by M2, then of course this coefficient becomes 1, and K1 tilde over M1 tilde is just omega 1 squared. And for the same thing for the second one, omega 2 squared. So these 2 equations are identical, except that we have divided by M1 and M2 and use the fact that omega 1, the first natural frequency, is the square root of K1 tilde over M1 tilde. Okay? So what we're going to do is, because we know that there is, in a realistic problem, there is a damping involved, and based on experience that we have, damping is something obviously less than 1, because otherwise it's not a underdamped system. Basically, it doesn't oscillate. So typically for structure, the damping maybe 0.05, 0.01, something like that. It can be higher. It's just that I'm talking about typical values, realistic values. So what we do is, this is what we get. Notice that we just threw these 2 in. This 2 zeta 1 omega 1 Q1 dot, this term and this term is just thrown into that mother of all equations that you saw in the previous slide. Okay. Each one of these is a single degree of freedom system, and if you go back to your notes from week 3, you see that we actually have a solution to that equation. The top equation, there's only one variable in it, Q1 actually, okay, Q1, and these are all constant, and we have the solution to this being in that form. Now, of course, little d1 in the front is and little phi1 in this argument. These depend on the initial condition, and the same thing with the second equation. You look at the second equation right here. The solution to this is right there, okay? And d2 and phi2 depends on the initial conditions. Okay. Now, there is an omega d1 here and omega d2. These are the damped natural frequencies. So for the first mode, natural frequency is omega 1. Remember, we don't say omega n1, we just say omega 1. Omega 1, and it's the same formula that we had from the week 3, because this is essentially the same kind of thing that we did in week 3. It's a single degree of freedom system, so everything that we did there carries over here, except that instead of one natural frequency of two natural frequencies instead of 1 degree of freedom, Q x1 and x2 that we had back then. It's going to be Q1 and Q2, etc. All right, so that is the template from week 3. So this is what I used just now to show you what the solution is. Remember there we had this thing, and if you divide it by m, it looked like that, equal to 0, right? And I mean, the template said that the amplitude is A. Here I'm going to say D1 and D2, so generally D, okay, little scalar D. There it says we have a phase angle theta. Now we have phi1 and phi2 because there's two such equations. Everything is the same, and except that in that template, instead of A, there's the D, and instead of theta, there is phi. Now, remember, the initial conditions will tell you what the little d and little theta is, or A and theta is. And in it, I have the initial displacement and initial velocity for each of the modes. So if you look at down here, you have to write d and theta twice, once for the first equation. That's why for the first equation, I have q1 dot instead of x naught dot. Okay? So, and instead of x1, I have q1 at 0. So what you see here is exactly the line up there, except that it's written for the first equation, and it's written for the second equation. For the first equation, anytime you see an x, it's q1. For the second equation, anytime you see an x, it is q2. Okay? So nothing new here. It all goes back to a single degree of freedom system and the fact that we know how to decouple our equations. Okay. We will do examples in a few minutes, but let's see now. Q1 and Q2, let me remind you, Q1 and Q2 are the modal coordinates, and they're related to the physical coordinates through this matrix P, which is called the modal matrix. So first you have to find the natural frequencies. For each natural frequency, you find the corresponding mode shape. You put it in the columns of the P matrix, and there is your modal matrix. And if you look at this thing in a slightly different way, although there's nothing wrong with it, it's just that if you view this thing as that column times Q1 plus that column times Q2, and you can just multiply these out, you see that you get exactly what you have up there. Then basically we have the stuff that we discussed 2 days ago. So we have the mode shapes times Q1 and Q2. Now remember, Q1 and Q2 are these expressions which have D1 and D2 and phi1 and phi2 in it. So here, because I'm using the summation notation, instead of saying D1 and D2, I said Di, I going from 1 to 2. And zeta I and omega I and omega di, which is the damped natural frequency for mode I in general. Okay, so let's do an example. This problem looks familiar to you. These numbers look familiar. And the reason I use these numbers, because I don't want to go through this calculation and find the frequencies which are right here. We did it, and the mode shape. We have already done that. And in the event that you have something like that on the test, and you see something that was already done for you, you can use it. You don't have to go start at ground zero, because there are other ways for me to test you to know whether you can actually find these things. Okay, this and the mode shape. So suppose that the first mass has a damping ratio of 0.05, and the second one damping ratio of 0.1. Okay, and some initial conditions are also given to you. So the first thing is to get the decoupled mother of all equations, and that is done through the stuff here. These were the frequencies that we had to find, and since we have already done this problem, I just took them. And these are the mode shapes which you have to find patiently one by one. Get these mode shapes, put in the matrix P, and you get your modal matrix. And you need the inverse of the modal matrix because we want to find the initial conditions out of these two. Okay. So here is the transformation. So the physical coordinate is the modal matrix times the modal coordinates, And if you, same thing, if you want to write it as with arrow, means these are vectors really. These are vectors. This is not scalar. X is x1 and x2. You can see that, and q is q1 and q2. So if you want to find qt, because you need to find initial conditions on q, you need to actually multiply this thing by the inverse. Because if you plug in t equal to 0 here, because you know x of 0, you can get q1 and q2 at 0. You need it. And if you differentiate this, okay, you differentiate this, you get q dot equal to p inverse x dot, and you put t equal to 0 in there, you have the components of q dot at time 0 in terms of the components of x at time x dot at time equal to 0. Let me remind you that the decoupled equations came out to be like that, okay? And in this particular problem, there's matrix M, there's the matrix K. This was the transformation, the modal matrix, and these were the modal mass matrix, and this is the modal stiffness matrix, and these are the things that actually went into this decoupled equation. Okay. Now, just keep in mind, this is in passing, that if you take ratio square root of 72 over 18, you're going to get the first natural frequency. If you take the ratio of the square root of the ratio of 36 over 18, you're going to get root of 2. So you should. These were the decoupled mother of all equation without any damping. If we have damping ratios of 0.05 and 0.1, just throw in an extra term here, which is 2 zeta omega q dot, right? Right there. 2 zeta omega q1 dot. And for the second equation, again 2 zeta, its zeta, omega, its omega, which is root 2 times q1 dot. So undamped, modal damping specified by the user. I have to solve these two equations by hooks or by crooks. Okay? By the way, you notice that this thing that's in the box, I've taken the guy on the very top here and multiply the top one by m1 tilde and the second one m2 tilde. So that's how you go from here to here. Actually, if you look at this term, you see this? You see this right there? You see this? This is the same thing, except that I've thrown in the damping terms, q1 dot and q2 dot. Okay, so here's the solution to the first equation. There's the solution to the second equation. These are the modal, the damp natural frequencies. And in order for me to find D1 and D2, phi1 and phi2, I need initial conditions. So here is the transformation matrix, Q relating to X, Q dot relating to X, and you put in T equal to 0. This is given to you, X of 0 is given, X dot of 0 is given, and so you just plug it in. This is going to be Q at time 0. So this is Q1 at 0, this is Q2 at 0, which happens to be the same. And you plug in T equal to 0 in there. And you're going to get, this is Q1 dot at 0. This is Q2 dot at 0. Because it was released from rest condition, obviously Q's are also going to be 0. There are other ways of finding these these coefficient D1 and D2, but I will use exactly what I'm showing you here. Okay, so these are the initial conditions in terms of Q, the mother of all equation, where damping has been thrown into it, and these are the initial conditions that you got from the previous slide. So basically, you find your D1 and D2. Well, first of all, let me actually just plug in the stuff here. So remember, this is the first mode shape, the mode shape times Q1. This is the second mode shape times Q2. Okay. Remember the modal matrix? The modal matrix was 1 and minus 3 and 1 and 3. So wrote these, and now we're going to use initial conditions to find D1 and Phi1. And I do it with the MathCAD. You know, basically there's a lot of punching in. So you find D1 and D2. We have the formulas for them, Phi1 and Phi2. And these are the values. And you plug it into the formula for X1. Notice that both frequencies are involved. Both the first natural frequency and the second natural frequency are involved. Okay? And you have plotted them here for you. Okay, so this is X1 and this is X2, and we just solved a free vibration of a 2 degree of freedom system subjected to some prescribed initial conditions. Okay? Okay, very good. Now to show you that actually this is from 0 to 42nd, but if you zoom in to a very short interval here, the reason I did that, if you look at X1 and X2, both of them have zero slope. One starts up there, they are zero slope. They better be zero, because remember, one of the initial conditions was that the two masses are released from rest. So the derivative, there was no velocity. The derivative of X1 as a function of time and the derivative of X2 as a function of time better be zero. You cannot see it in this diagram. In these diagrams, you cannot see it, but it actually, for example, if you look at this, it starts and it builds up. Start with zero slope, it builds up. And over here, start with a zero slope and build down. Okay, so although this modal damping is fine and it's widely used in practical applications, there is an alternative approach called the Rayleigh damping strategy. In other words, now notice that first of all, M and K, I know how to, if I ignore damping, if I ignore this middle term, I can make a transformation which M becomes diagonal and K becomes diagonal. That's what we did on Thursday, and I did earlier today. However, if in general there's a matrix C here, that transformation which makes this diagonal and this diagonal, and that transformation is simply X equal to P times Q. So X equal to the modal matrix times Q. But there is no guarantee if I use that transformation that this matrix actually is diagonal, C is diagonal. And that kind of bring us to a full stop, because the whole idea behind what we did for the last week or 2 weeks or so was that we decouple the equation. If we cannot diagonalize this with the same matrix, same transformation, which diagonalizes M and K, well, we can't proceed any further. The whole idea is to decouple these. So if these are diagonalized through M tilde and K tilde, this better be diagonal too, so that these equations are decoupled. One way of guaranteeing you that actually this matrix C can be diagonalized with the same transformation is to pretend C is the sum of, or a multiple of, the mass matrix and a multiple of the stiffness matrix. This is called structural damping or Rayleigh damping. Okay, Rayleigh damping. Our textbook calls it proportional or Rayleigh damping. Forget about that structural. In our textbook calls this thing proportional or Rayleigh damping. Alpha and beta are constant. M and K you have. Alpha and beta constant. And if you look at this thing, the unit of this alpha is 1/2, and unit of beta is second. Okay, so this is just a comment. Okay, so if we have C like that, we are guaranteed that the whole system of the two equations can be decoupled from each other. Same transformation. Okay? Good. So what we did, we take the X, this was the X, we plugged it into the mother of all equation right there. So it becomes PQ double dot, PQ dot, PQ, and pre-multiplied both sides by P transpose. We know already this is going to be diagonal, and we call this thing M tilde. We know this thing is going to be diagonal. We call it K tilde. And this thing, because of the way that is, because this is diagonal and this is diagonal, when you multiply on this side by P and on the left by P transpose, then that C tilde also becomes diagonal. You understand? Look at what's, we are multiplying C on the right by P and on the left by P transpose. If you go and do that in this line, if you multiply M on the right by P, on the left by P transpose, that becomes diagonal, and we call it M tilde actually. And if you multiply the same thing, multiply this K by P on the right and P transpose on the left, this became diagonal, and we called it Q tilde. Two independent, decoupled, second order equation where damping has been included. So, for each one of these, we have a damping ratio. It goes back all the way to the single degree of freedom. If you master single degree of freedom solution or concept, multi-degree of freedom is simple extension of that. So these are all things from the single degree of freedom system for mode 1 and for mode 2. Okay? This is how this transformation that we did, the C tilde, was actually alpha M tilde plus beta K tilde. Because remember, this on the right was multiplied by T, M on the right was multiplied by P, and on the left by P transpose, and that's what we call M transpose. So anyway, there it is. So you notice that this C1 and C2 we have there, which we have there, is actually a combination of these two. Okay? Because these are diagonal. Just write this thing down literally. This C1 is alpha of that plus beta of this. And this C2 is alpha of that plus beta of that. Okay? So the question may be, how do we find this alpha and beta? Well, okay, so what do we take this C1 and C2 out of these two, C1 tilde and C2 tilde out of these two, and plug it in our equation? In other words, if you let me show you something here. First of all, if you look at this expression, okay, if you look at this expression, and you divide, for example, both sides of this thing, okay, if you divide both sides of this thing by this top equation by 2m1 omega 1, if you divide that equation, top equation, this equation, if you divide it by 2m1 tilde omega 1, you're going to get this equation. Just try it. Just try it. Divide this by 2m1 tilde omega 1. You're going to get this equation. You divide the second equation by 2m2 tilde omega 2, you're going to get this equation. Literally, you have to do it. Just do it and figure it out. Okay? All right. So this damping ratio that we have, in general, as a function of alpha and beta, it looks like that. For psi 1 is this, for psi 2 is like that. So generally, it follows this form: alpha 1 over 2 omega plus beta omega over 2. Okay? Okay. So let's move on. Now, this expression that I have for you, zeta, in terms of frequency. Let me go back here for a second. See that? Zeta as a function of frequency. So these are constant. Alpha is a constant, beta is a constant, 1 over omega plus essentially omega, okay? So if you look at this, if you plot that, it's going to look a curve like this. Notice that when alpha is 0, zeta is simply beta. If alpha is 0, let me go back here. If alpha is 0, zeta is simply beta times omega over 2. So it's a linear function of frequency, right there. This is the case where alpha is equal to 0. On the other hand, when beta is equal to 0, then that linearity goes away and you're going to have zeta equal to alpha times 1 over 2 omega. Now, I don't want to go back to the previous slide, but if you do that, you're going to get a hyperbola like this. So this corresponds to where beta is 0. That's why your damping is essentially, your damping matrix C is just alpha times M. That's why it's called mass proportional. And this corresponds to the case where alpha is 0. So if alpha is 0, your damping matrix is just going to be beta times K. That's what is called stiffness proportional damping. So when alpha and beta are both present, you're going to get what is the combination of the two, which is that curve here, namely alpha times 1, let me see now, alpha times 1 over 2 omega plus beta times omega over 2. So it's going to give you this curve, okay? So this is a general Rayleigh damping case. Now you might say, well, wait a minute, how do we know if we have Rayleigh damping? So if we have a situation where parallel to every spring there is a damper, parallel to every spring there is a damper, and the ratio of this damping to that stiffness, ratio of this damping to that stiffness, these are all the same. This over that, this over this, this over that, they're all the same. Then we have the case of basically the case of let me see now here, we do have a Rayleigh damping, but let me see, this case is when stiffness proportional, right? So because look at what happens here. If this ratio, this over that, this over this, these are all the same, we are dealing with a case that we have a stiffness proportional damping. And for the other one, where at every parallel to every spring there is a damper which is grounded, then we have a mass proportional damping, okay? So this is a mass proportional damping case. This is a stiffness proportional damping case. But remember, you also need the ratios to be the same. This over that, this number over that number, this over, they must all be the same. Now, the one problem with the mass proportional damping, you might say, well, why don't I set always alpha equal to 0 and work with the case of beta times K? Or why don't I always put beta equal to 0 and always work with alpha M? Now, to work with alpha M alone is not really what happens in real life, because if you look at this thing, if you look at the case where beta is 0, so we are dealing with this case, mass proportional damping right there, beta is 0, we get this. It says that at high frequencies the damping is very small. Actually, real life is the other way around. Very high frequency are damped very quickly. Okay, I'm sorry, that's not what I meant. Very high frequency have a large damping, which means they kind of disappear very quickly. So large frequency should have in real life a large damping coefficient. Okay, whereas this is showing you the other way around. that's why just working with mass proportional damping, it may be convenient, but it's not very good. And the same thing, of course, is true with the stiffness proportional damping, because, you know, stiffness proportional damping does actually what it's supposed to. Large frequencies are damped very a lot, okay? However, the best, it seems that the best case scenario, some experimental results indicate that you have to take combination of the two. So here's an example. It's the same problem as we did before, same one, except that I am not giving you zeta 1 and zeta 2. I'm giving you the coefficient of Rayleigh damping. So alpha is 0.25 and beta is 0.5. So let's stick to these values and see what the result is going to come out. Now, the initial steps are identical. In other words, first you have to find the natural frequency. It's found here. We did this problem many times in the past, so we're just going to take it for granted. These are the frequencies. This is the modal matrix. The inverse of the modal matrix. The decoupled equations right here. Undamped decoupled equation. These are the same slides from the previous example. Here's the MathCAD worksheet. So if you have alpha and beta, then you go and plug it in here. Zeta 1 is just plug in omega 1. Zeta 2, just plug in omega 2. And you're given alpha and beta, and you're going to find zeta 1 and zeta 2. Okay? Remember, alpha and beta are given to you. The coefficient of Rayleigh damping are given, and then you just plug it in the expression, you find the zeta 1 and zeta 2. Then in the previous example, what I said is, here is zeta 1, 0.01, and zeta 2 is 0.05, or something like that. Here, you're given the coefficient of Rayleigh damping, and then you have to find zeta 1 and zeta 2 accordingly. So the rest of the steps are identical. We get the decoupled or diagonalized mass matrix, diagonalized stiffness matrix. These are called modal mass matrix, stiffness mass matrix, modal mass matrix, modal stiffness matrix. Again, remember that the ratio of 72/18, if you take the square root of it, you get natural frequency, and 36/18, if you take the square root of it, you get the second natural frequency. These are the undamped equation, and here all I've done is divided by 18, doesn't matter. Now, we found, based on the calculation in the previous slide, zeta 1 and zeta 2 are these. And so just throwing your damping terms with these coefficients, zeta 1 and zeta 2. And this is the equation. These are different, obviously, from the previous example, because zeta 1 and zeta 2 were there, they was given to you. These numbers were different, okay? This box, once again, comes from exactly this expression, except I multiplied both sides by 18, M1. In this case, both are the same, M1 tilde and M2 tilde, both 18, so you get this. And find the initial condition. Nothing changed from the previous case. This is exactly the slide from the previous example. And the only difference is that when I go to my MathCAD worksheet, instead of zeta 1 and zeta 2, which I had in the previous case, I'm putting what I got from Rayleigh damping. And then you get your x1 and x2, and you can plot it. You can see that these are based on the value of alpha and beta provided. It has a completely different spot. Now, don't get the impression that therefore these are always different. Of course they're different, but dramatically different from if you give modal damping. Now, if I had given you in this problem, instead of alpha and beta, I have told you what zeta 1 and zeta 2 are, you would not have realized that this is coming from a modal damping or from a Rayleigh damping case, so you would have just used the previous example with these current values of zeta 1 and zeta 2, and you would have been happy, okay? So there's some final comments about Rayleigh damping. In practice, you find zeta 1 and zeta 2 from experimentation, okay? Notice that here I gave you, in this example, I gave you alpha and beta, and I asked you to find zeta 1 and zeta 2. So in practice, you get zeta 1 and zeta 2 for two mode shapes, important mode shapes, from experimentation, okay? Now, once you do that, you plug it in that equation and you find alpha and beta. So we did things in reverse order. I gave you alpha and beta, I asked you to find zeta 1 and zeta 2. Here, I'm saying that in real life, you decide on two important frequencies. And they don't have to be consecutive, by the way. Two important frequencies. And from experimentation, and these can be done from logarithmic decrement stuff that we did back in week 4, week 5, something like that. And you find alpha and beta. So alpha and beta, and there is no physics. The only reason we actually did this is because we were able to diagonalize with this choice, alpha m plus beta k, we were able to diagonalize the damping matrix. There is no physics behind it. It works as long as you get these things from experiment, and as long as you're happy with modes in between to be damped the same way. Okay, basically we impose the damping on the entire structure based on only two frequencies. Okay, so the question is now, what about a forced response? So we have mass matrix, stiffness matrix, damping matrix, but the right-hand side is not zero, it's not a free vibration, it's a forced vibration. Now, without this middle term, with c equal to 0, we did this thing last Thursday. So now we're going to include this. This strategy is the same. Diagonalize, decouple. So remember, you can write this thing in the vector form if you want, doesn't matter. And obviously this is coming, I mean, getting this thing is important. Why is that the case? You go back to a single degree of freedom, look at the free body diagram, mass x, and the acceleration, etc., and you get this equation. So literally, you should be able to sit down and, based on the diagram here, come up with the mass, in this particular case, with the mass matrix, stiffness matrix, and the what is it called, the damping matrix. Okay, so please make sure you can, by yourself, you can figure out that the mass matrix is obvious, but the stiffness matrix, just make sure you can sit down and work these out. So, for example, remember this K12 and K22 and K11, etc., are related to these things. So you have to, just specific problem, you have to work those out. So the transformation is the same, okay? And put this thing in there, pre-multiply by P transpose, you get this. This is your diagonal mass matrix, modal mass matrix. This is your diagonal stiffness matrix, modal stiffness matrix. This thing is going to be your diagonal damping. And we know when this is going to be damping. For example, either you enforce you pretend that you just throw in two zeta I, omega I, omega I, just plug it in, pretend that you plug it, or you use the, for example, Rayleigh damping to come up with the appropriate diagonal damping matrix. So the bottom line is that this is a diagonal, and the right-hand side. And these are decoupled equations. Okay? We did this thing on Thursday, except that there was no middle term. And I told you that this right-hand side, you can look at it like either, this actually is a mistake. It should not be like that. This is a mistake. It should be U1 dotted F bar or U2 dotted F bar. If you put a transpose here, just take away these dots. Okay? Take away these dots. Good. So if you take these equations, write it in detail, I've done that here, and you divide it by M1 for the first equation, this coefficient becomes 1, and you get the standard form. You divide this thing by M2, this becomes standard form, and once again, either you take away the transpose, or if you're going to put a dot here, don't put the transpose there. Okay. Now, stuff like this, we have the solution. And notice that these equations are forced damped response equation. And we have a solution for it. Yeah, if you ever have something like this from back in week 4, 5, okay, we can write the solution in terms of the impulse response function, if you want, and the convolution. Remember the convolution, this is the Duhamel integral, convolution integral. And if there are initial conditions, of course, you have to throw it in right there. This is the Duhamel integral. Remember, these are the impulse response function, but the one for the damped one. And if there is no damping, of course, this e to the 0 is not there, and all these omega t's are omega d's, omega n. Okay. So let's do an example right here. Same problem. Coefficient of Rayleigh damping are 0 and beta equal to 0.1. And there is a force, sinusoidal force applied to mass 2 right there. There is an FT, but it's applied to mass 2. I mean, incidentally, it couldn't be both masses, but here I'm going to do mass 2. So this was the mass matrix, the stiffness matrix. We found the frequencies, and now we're told that this uses Rayleigh damping. So alpha is given as 0 and beta is 0.1. No problem. So if you do that with this information, you come up with the damping matrix, which is this. We need the inverse because well, if we have initial conditions, we need the inverse here. Let's move on. Yep. So mass matrix. This is before we diagonalize. You can see that before we diagonalize, these are coupled. Mass matrix, damping matrix, stiffness matrix, and the right hand side. Okay. So we make a change of variable. Okay. We get the modal mass matrix, modal stiffness matrix, modal. Think about it as modal damping, although we got it from Rayleigh damping. And P transpose F, you have to do that. You're going to get this. You find your, because you're going to have to solve this thing, you're going to have to find the natural, damping ratios for each one of them. These are the damped frequencies. These are the decoupled mother of all equations. You can see that right there. And the solution is going to look like that. And A1 and Phi1, A2 and Phi2 depends on the initial conditions. Now, this is a template from there, and notice that in this problem, let's continue with this for a second. Now, what I'm going to do here, let me see for a second, some initial, this particular problem, let me go back for a second. I'm not giving you any initial conditions, but what we are doing here is we are finding the, can I go back for a second? I'm really sorry about this. We are asked to find the steady state response. Steady state response. Steady state response means don't worry about the initial conditions. Okay. This is why we will not need this P inverse because there are no initial conditions given. But and let me see now. I made a mistake. I made a comment here. Wait, let's go back. I made a comment here that this A1 and Phi1, A2 and Phi2 depend on the initial condition. I'm really sorry. This is the steady state response that we're talking about. And go back to your note from a steady state response of a harmonically loaded single degree of freedom system. You see that these things, there's no steady state. There's no initial conditions built into them. These have to do with the formulas that we had from back then, right, for the amplitude X. See that? The amplitude X, stuff like that. And if there is damping, of course, X is going to be a bit more complicated. Here it's right there, right there. These are things that we did 5 weeks ago. Okay, let's move on. So we just plugged in these expressions. There's no initial conditions involved here. You just have to literally plug it in. Remember, the other way of writing these things were in terms of R. Do you remember that? In terms of R. So this was 1 minus R squared squared and 2 zeta R squared. But here it's written in terms of not R, in terms of omega and omega 1. This omega is the driving frequency. This omega 1 and omega 2 or the omega 1, and in the next line omega 2. See that? These are the natural frequencies, which was in one case 2, the other case was root of 2. And you can plot it. Okay. Notice that I never needed P inverse. Yeah, so last item that we want to discuss today is to show you that one has to be careful about dealing with resonance in 2-degree of freedom system or in general multi-degree of freedom system. Now let me remind you that in the context of a single degree of freedom system, resonance meant that if the frequency of the applied load matched the natural frequency of that system, in the case of undamped system, for example, the amplitude of the vibration went to infinity, or in the case of damped system, you had a large amplitude. So this was the case for a single degree of freedom system. In the case of 2-degree of freedom system, there's 2 modes here, okay, and one has to be a little bit careful about just saying that, oh, if the driving force has a frequency which matches the natural frequency, then we have resonance. That may or may not be the case, as you will see later. Now, let me read this thing. It is important. The concept of resonance in multiple degree of freedom system is similar to that introduced in single degree of freedom system. It is based on the idea that the harmonic driving force is exciting the system at its natural frequency, causing unbounded oscillation in the undamped case and response with maximum amplitude in the damped case. But, however, in multiple degree of freedom systems, there are many natural frequencies. For us, there is 2 because we are looking at 2 DOF. And the concept of resonance is complicated by the effect of mode shapes. Basically, if a force is applied orthogonally to the mode of the exciting frequency, the system will not resonate. And I'll mention that to you as in the context of an example. All right, so let's take these 2 cases. We have a problem like that. The right-hand side is harmonic. Frequency 2 radians per second. Case B is a different vector here, load vector, you can see that, times a frequency which is right here. Now, this is not the same example that we were doing before. Remember, we looked at this one example, the frequencies were 2 and square root of 2. This is not the same problem because the data that I'm going to give you is going to be different. So, for example, 4 kilogram, 2 kilogram masses, these are the stiffnesses. I could have used the same example as before, but since you should be able to find the natural frequencies and modes, it's a good idea to be able to see a new problem so that you can try it out, see whether you can get these things or not. But I could have used that same example. Now, here's the mass matrix. Here's the stiffness matrix. Okay? And first, let's find the natural frequencies. Be prepared for things like this on the final exam. So this is the characteristic equation. And if you solve this thing, you get 2 frequencies, 0.676 and 2. etc. 75 ... And for each one of them, you should be able to go and patiently find the modes, mode shapes, right here. So this mode shape goes with omega 1 right here. This mode shape goes with omega 2 right there. There is the modal, there's a modal matrix. You take these, put it in the columns. I don't need the P inverse, but I just calculated it there for your convenience. If you ever needed it, For example, if you had initial conditions and things like that, you're going to need this, but in this particular problem, you want to look at the effect of resonance. It has nothing to do with initial conditions. Now, let's look at the first case. So the load has this frequency 2, which is neither one of those natural frequencies, incidentally, and it has a load vector which looks like that. So let's actually go ahead and diagonalize the stuff. So here is the problem, and for convenience, notice that I'm not taking any damping. Now, obviously, damping is damping. Even if you had damping, the concept of resonance is independent of that. It's just convenience. So I need an I need to diagonalize this. So remember, we did it like this. We made a change of variable, and by saying x equal to pq, and we replaced x with q, and then we pre-multiplied by p transpose, so you get this. These are decoupled equations, you know that, and in fact I've written it down here for you. So there is the modal mass matrix, this is m tilde right there. This is the modal stiffness matrix, k tilde, notice that they are diagonal. And this thing, remember, it was p transpose times f. We already had f, we put the p transpose, you get this guy. Okay, good. Now, this right-hand side or that right-hand side does not match either one of these two frequencies. So definitely we're not dealing with the resonance case to begin with. No problem. Now let's go to the other situation. The right-hand side looks like that. Okay. So here is the original equation. This is the decoupled equations. Same thing as the previous slide. And just literally wrote them down. So there we are. Now obviously these two don't change. It's just the right-hand side changes. This thing does change. We like that. So if you take the p transpose and multiply it by this f, you're going to get this. And the driving frequency now, you can see that, is actually matching the natural frequency. Okay? So, but this will not cause resonance, and I will tell you why and what I mean by that. Now, notice that the key is this. The vector of force distribution. This is the vector of force distribution right there. If it's orthogonal to the second mode shape, this is the mode shape 2. This is the frequency 2, modal frequency 2. And the mode shape of that is the second column of that modal matrix. It says if this vector is perpendicular to the second mode shape, because that is the second mode, right? Second natural frequency. So here we are. If you look at the first one, first column of that matrix, dotted with f, this is not 0. But if you take U2, this was U2, this was the second column of P, dotted with this is 0. And that is why this will not lead to resonance. Okay? Now, it is important to state that if the vector of force distribution in case P was anything else, so that that guy would not be 0, okay, you would have a problem. For example, if you take this, instead of whatever I gave you, if I told you f of t was 1 and 0 times this, you got a problem. Okay? Because the product of the second mode shape with this is not 0. And there will be resonance. And therefore, the most common case of resonance in the driving frequency is near a natural frequency. Okay, so unless that f is selected in very special way, you may not have a resonance case. But generally speaking, that is not the case. And if your natural frequencies matches the driving frequency, unless it was done by design, you should expect resonance, just like in single degree of freedom system. And that takes care of the presentation for today.